All right, today we're going to talk about valence electrons and Lewis dot diagrams. So to start, we need to explain or re-explain what exactly valence electrons are. And so we're going to start with, let's say, we're going to start with, let's do fluorine out there. Fluorine has, what is the electron configuration for fluorine? Let me throw our periodic table back at you. Okay, so fluorine is right there. Okay, so for fluorine, we have 1s2, 2s2, 2p5. Okay. And then how about chlorine? How about the one under it? It's going to be
1s2, 2s2, 3s2, 3p6, 3s2, 3p5. Yeah? Question? Okay. So here are your valence electrons. We defined them earlier. Okay. Our valence electrons are the highest energy level S and P electrons. They're the highest energy level S and P electrons. So for fluorine, okay, the highest energy level S and P electrons would be those and those, right? Yeah, because S's and P's, and this is the highest energy level. 2 is the highest energy level. And these are the S's, and these are the P's. So together, fluorine here, and we do this to determine the number of valence electrons. And so this would be 2 plus 5, giving us 7 electrons. Yeah? So here's our S. How many electrons are there? 2. Here's our highest level P. How many electrons are there? 5. 5. 2 plus the 5 is 7. Okay. So for fluorine, and so for chlorine, the next one, we're looking for the highest energy level S and P electrons. Our highest energy levels would be 3, and those S and P electrons would be 2 and 5. Again, 2 plus 5 equals 7 electrons, and those are our valence electrons. Yeah? Okay, we're going to do one more, and we're going to do selenium. Selenium. Okay, selenium is number 34. That will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p. 4. How many valence electrons does selenium have? Okay, we are looking for the highest energy level S and P electrons. The highest energy level are these 4s, right? How many S and P electrons are there? 6.
2 plus 4 equals 6 electrons. Those are valence. Yeah?
Yep.
Okay, so what is RGDP electrons? Okay. By the way, if you don't have your periodic tables out, get them out.
This is the time. This is when you need them. Okay, so what if we do calcium? That's kind of hard to see, isn't it? Okay, we do calcium. Calcium's number 20, right? All right, so that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and that's it, right? So how many valence electrons is it going to have? Just 2, right. 2 electrons. There are no p electrons, so we don't count those. Okay, so essentially what we're looking at is we're only looking at those outermost electrons, right? Only the ones that are on the outside, the highest energy level electrons. These valence electrons we draw in what's called a Lewis dot diagram. And so we're going to draw these diagrams. We're going to do fluorine first. But we're going to draw them as if we were filling up the electron configuration boxes. Remember those? The up-down arrows and... Okay. So if we're going to fill in this 2s2 box, because that's going to fill in first, right? Those electrons would go in the same orbital first, right? So we're going to draw these dots as if they were around our fluorine atom. So we're going to draw the first two together, and it doesn't really matter whether you do it north, south, east, or west. The first two go together. And then how many do we have left? Then we have the other. Okay, so these are the S2s. And then we have the other 5, right? Now, technically, you should draw them 1, 1, 1, and then you double up, right? Because we need to obey Hund's rule. Okay. But I don't really care if you just draw them together. I'm assuming that you understand Hund's rule and they go in pairs. And that. So this right here, this is the Lewis dot diagram for fluorine. Yes, Alicia.
I thought that the Lewis diagram was like that. If you start at the top of F, there was no way for the other one to have 2 dots when you skip that one.
The other 5. Well, remember we only have 5, right? So fluorine would look like. Here's that box, right? And then here's these 3. And then these would have up, down, up. You wouldn't do it like that. Up, 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 and then down, down, right? Okay, but you have to put 1 in each before you have partners. Yeah? Okay. At this point, I'm assuming that you know how to do this. And so when we come over here, it's okay to put the first 2 together and then just draw the next 5. As long as you only have 2 on each side, no more than 2 on each side, you're going to wind up with 1 empty one because you only have 7 electrons. Does that make sense? Yeah. Okay. So let's get rid of that here. Okay, so this would be the Lewis dot diagram for fluorine. It's got 7 electrons. There you go. How about chlorine? What's chlorine going to look like? It's going to look exactly the same. It's got 7 electrons, and so it's going to have 1, 2, 3, 4, 5, 6, 7. Notice the space is in a different place. because it doesn't matter. As long as you have 7 electrons around it and they're in pairs, okay, you're going to have a space. This is going to have 7 electrons around it. Yeah? Okay, selenium. What's selenium going to look like? It's going to have 1 less. 6 electrons. 1, 2, 3, 4. Now this is where it is sort of important. These next 2 don't go together. They do stay separated because of the whole Hund's rule thing. Yeah? It is Hund's rule. Yeah. And then finally, calcium. Calcium's going to have 2. And that's it. When you're putting in your right, and you're putting in your electrons, your first 2 go together, and then it would be up, 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 down, right? Space, space. Yeah? On selenium.
Why are those 2 dots separated, but on calcium they're together?
Okay. The first 2, these are the S2 electrons, right? That's what the S2 electrons look like.
Okay.
So they go together. Now, you will see if you look this up in your book or maybe online you're doing your own research, you might see calcium and they separate the electrons. It's not technically wrong. It's just not consistent with what we've already learned. Yeah? We learned that the first 2 electrons, the s electrons, go together in an orbital. We've learned that. When you draw the Lewis dot structure, I expect you guys to draw the first 2 together. When we start, and you'll see here in a bit, when we start bonding them with other elements, you're going to have to break these 2 up. It happens. That's the way it goes. Okay. All right. Okay. One of the characteristics of bonding is all elements want to look like a noble gas. Okay, so that's the everyday statement. The specific statement is all elements so all elements gain, lose, or share electrons So all elements want to look like a noble gas, and that means that all elements will gain, lose, or share electrons in order to achieve an S2P6 electron configuration. Because if you look at neon, let's take a look at neon. Neon's electron configuration is 1s2, 2s2, 2p6, right? Okay. And then argon beneath it is 3s2, 3p6, right? And then krypton beneath it is 4s2, 4p6. And beneath it is 5s2, 5p6, and 6s2, 6, right? All of our noble gases have this full s2p6, and that means it's going to look like ta-da! It's going to have all of its electrons full. This is a noble gas configuration, and this is highly stable. HIGHLY, not Higley, highly. Remember when we talked about potential energy? And so if you have this we have this hill. And we have a boulder on the hill. Okay. And we give the boulder a little shove. Just a tiny one. What's the boulder going to do? Okay. It's going to roll down the hill, right? Okay. Why? Okay. Let's pretend that right here is Jasmine's hand. Okay. Jasmine's hand is at the bottom of the hill. What do you think is going to happen when we push down the boulder? It's going to roll down and it's going to smash Jasmine's hand because that's what we do in here. All right. That means, what did this have? Why did I reference Jasmine's hand? That means this boulder up here has what? It has potential energy. Okay. Now, it could roll down, but notice that this hill up here is higher than this hill, yeah?
Yeah.
So this hill up here would have more potential energy. Yep. So if I push this boulder down and it rolled back up the other side, do you think it would reach up here? No, it couldn't do that. It's only going to reach as high as the original amount of energy that it had. You know, it's kind of like if you bounce a ball. The highest it could possibly go is backed up to where you dropped it to begin with. But even so, it's not really going to do that. It's only going to, because it loses some in the way of friction and some internal heat and that sort of thing. Well, okay. When an atom gets an electron configuration, that looks like a noble gas, it is as if it's at the bottom of the hill. What's that? That is a noble gas electron configuration, S2P6. Am I off the screen? No, almost. This right here would be an S2P6. Okay, it's at its lowest potential energy level. It's very stable. If you try to push this boulder out of the well right here, it's going to take a lot of energy to get that boulder out of the well, yeah? Okay, imagine this boulder represents an electron on an element that has this noble gas configuration. You're going to have to give it energy to get out. Yeah? That amount of energy that you have to give it to get out is the ionization energy. And we talked about ionization energy before. That amount of energy to get this out of the well is the ionization energy. It's how much energy you have to give that electron to get it off the atom. Yeah? Okay. Up here is S2P5. And that one's P4. And P3. And so on. Up, and mind you, they go all the way up till you get to S1, yeah? Okay, and S1 is right there. It's right at the very edge. And so it would be easy to take that S1 electron away. Yeah? Okay, so now I want you to think about that. Let's say we're going to take one of our elements that has this S1 electron. So we're going to take potassium. Okay, potassium. What is the electron configuration of potassium? Potassium is 1s2, 2s2, 2p6, 3s1. Yeah? Right? No, more than that. 3s2, 3p6, 4s1. There we go. Okay. That S1 is way up there on the hill, yeah? It's way high on the hill. It's almost over the top. So we give it just a little bit of energy and that electron goes away. Yeah? Okay. What happens if we take away that one electron? Look at what's left. We have an S2P6 electron configuration. Yeah? So this is the potassium that's lost an electron, minus one electron. It has a stable electron. It's happy like this. It wants to be like this. It wants to shed off its skin. Or its clothes or whatever. Depending on whatever metaphor you want, it could be a molting snake. It could be your first day of summer. But here's the point. Here's the point. It only lost an electron. What does it still have? It still has the same number of protons. Potassium has 19 protons. After this, it only has 18 electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. Plus that 1 was 19, but that 1's not there anymore, so we're back down to 18. What's our total charge? We have a plus 1 charge. This is potassium plus. This is a positive ion. Also known as a cation. Okay, and I have that big T in the middle because it's a plus. Cation, that's how you remember. We have a cat ion. Because it's the cat ion. The should remind you of the plus. Okay. We're going to do this the other way. What was chlorine again? Chlorine, we're going to take this. I want to. I can't. Okay, there's our chlorine. Okay, this has 17 electrons. And it has, so 17 electrons, 17 protons. What is this going to take to get a noble gas configuration? It's at S2P5. What's that, Ian? We're going to add one. It's going to find, somewhere out there, it's going to find an electron, and it's going to add it to its electron configuration. So all of a sudden, we're going to get 3p6 if we add one electron. To our balance sheet down here, we're going to get 18 electrons rather than 17.
Which makes it a negative charge.
Which also makes it attractive to potassium.
Okay. It doesn't make it argon, but it has the same electron configuration as argon. Yeah? Same thing as potassium.
How do you tell the difference?
Because it has the same number
Protons.
of protons.
The protons don't change. This means it's still chlorine. This means it looks like argon.
Changes it to like an ion.
But if we have 18 electrons and 17 protons, this is now Cl minus. This is a negative ion, also known as an anion. Okay, question was, is there going to be a time where we have to add or subtract protons or neutrons, and that'll change our element? And the only way that happens is if, let's say we take our carbon-14 here, and carbon's going to have 4 electrons around it. This would give off a beta particle, and which is a nuclear electron which has way too much energy to be contained inside the valence electrons. And that would give us 14,7 nitrogen. But this nitrogen is now going to have 5 electrons around it. So where does that electron come from? Well, it doesn't come from the beta particle. The beta particle goes flying off. This actually comes from, and here's where I want to continue the lecture, this extra particle comes from other cations. So what causes these electrons to join, where these electrons come from, are when elements like potassium or when metals lose their electrons in order to look like their noble gas configuration. Yeah?
Yep.
Okay. And the strength of the chlorine wanting to attract electrons is enough to overcome the attraction of this last electron to stay around the potassium. And so it flies over and it creates our potassium. Okay, plus, which has this electron configuration now. Yeah? And we have our chlorine, which has this electron configuration now, but chlorine's a minus. They both have all the electrons they want, but this and this, they have opposite charges. What do we know about things with opposite charges? They attract each other. These two experience a pull towards each other, also known as an electrostatic attraction, that just because we have a positive charge and a negative charge and opposites attract, they lock eyes from across the room. And they're attracted to each other. And they don't actually, and they hang out with each other. They don't actually, the way they bind to each other is through this electrostatic attraction. And, ironically, we got another one of these. We got potassium, and we got chlorine. Okay, And to keep them a distance apart increases their potential energy. As the distance decreases, so does their potential energy. And so when they are at their lowest potential energy state, the distance between them is very small. Does that make sense? Okay. So the energy is released, they come together, and they create what's called an ionic bond. Okay. We're almost done. We're almost done. Oh, and that's the magic of video. Okay. So what happens? Calcium, what charge did... Calcium had a... What was its dot structure? It had 2, right? So it was a 4s2 that it finished with. Before that, it was 3s2, 3p6. That's what it wants to look like. So it's going to give up these 2 electrons, yeah?
Yep.
Okay. What if calcium comes in contact with, say, a fluorine? Okay, fluorine only wants 1 electron, right?
Yep.
Okay, well, when these atoms are actually in the... When these atoms are actually in the presence of each other, they're not alone. They're mingling with a whole bunch of other calciums and a whole bunch of other fluorines, which means there's enough of them that if there's 1 fluorine, there's probably another. In fact, there would be a bunch of both of them. Fluorine wants how many electrons? It wants a total of 8, and it needs how many more? It needs 1 more, right? Okay, we'll take a look. Calcium has 2 that it wants to give, yeah?
No.
Each fluorine wants 1. Okay, calcium gives up its 2 electrons, but they don't go to the same place. They go to 2 different, one of each of the fluorines, and so now we're left with a calcium that has a +2 charge because it gave up 2 electrons. We have fluorines and now we have each of these fluorines, each one of them has a -1 charge. But check this out. How many total negatives are there? 2.
There's 2 positives.
How many total positives are there?
2.
2. They balance, right?
That cancels out.
Oh, it doesn't have to be a 1-to-1 ratio. You can balance them in multiple ratios so long as your total charge is... So that you add up all the charges and they add up to 0. This would become calcium with 2 fluorides. This would be CaF2. This has to be subscript, just like the rules for electron configuration where you have to have the superscript. This has to be subscript. The A has to be lowercase. The first letter is uppercase, the second letter is lowercase. This can continue. You may, okay, there are times where you might need 3 electrons. There's times where you give up 2. There's going to be different combinations of these atoms, of these ions, in order to make their ionic compounds. Okay, we're going to stop there. We're going to move on to our activity, and we'll see you guys next time.